what do we mean by classic antennas? Anybody got any idea what that word means? I mean, what do we mean by the word classic? Think of classic cars and...
Old.
Oh, well, old? But what else does he mean? There are a lot of old things that you never heard of. Because what happened to them?
They weren't classic.
They weren't classic. So what makes them classic?
They're around.
They're still around. People are interested in them, right? So to me, a classic antenna is one that's withstood the test of time. It's been around for a long time and people still go back to them. And all you have to do is look at the latest MFJ catalog and you'll see some of these antennas that are 100 years old are being made by MFJ, you know, phased dipoles and stubs on dipole, all these sorts of things. Those are classic antennas. They've been around for a long time. What I find amazing in the history of radio is how much people knew 100 or 90 years ago. I mean, radio was pretty young. I mean, it went from really primitive stuff in around 1900 to by the 1920s in a decade. People learned a lot of stuff. In fact, some of the stuff they knew could put a lot of hams today to shame because they knew a lot of stuff that still turns out to be accurate. And a lot of these antennas come from that period of the 1920s and 30s or even older. And I find that really amazing that these guys with the equipment they had could make something work. And some of them were very clever. And there are so many kinds of antennas that fit into this category that we can't do justice to all of them. And you could see how long it took me to set up. This is only a fraction of things. I had a lot of fun building this stuff. You know, you read antenna books. How many people in this room have looked at a picture of a rhombic or something and drooled and said, I want one of those? Buddy? All right. Why didn't you have one?
Too big.
Too big! Right?
Acreage.
Acres. All right. Now that's the big guys have those. The guys that you hear about, like W1XX, people like that might have something like that. But most of us could only dream. Well, I decided I wanted to build a rhombic, and I did. The only thing is I made a miniature version of a rhombic so that I could carry it around with me. And the same with all these other antennas. These are portable antennas because of what reason? The size is tiny compared to what you normally would use. Because I'm doing this at UHF and not HF. I'm doing it at 432 megahertz, where a wavelength is 70 centimeters. There's 70 centimeters. Now picture a wavelength on the 80 meter band. 80 meter wavelength's about
240 feet.
Yeah, 200 and something feet. You're not going to carry these antennas around in this room for that band. But on UHF, if you could make a scale model, you can carry it around and demonstrate it. And then you can say, hey, this antenna is really neat. I like the way it works. And then may go out and build an HF version of it. But I'd rather put my effort into making something that I'm pretty sure is going to work if it's going to be that big. So I start out building stuff on these frequencies. And some antennas I really like. Some I find too complicated for what they do. And you'll see some of those. But there's some that are really simple and they work well. They want to work well. So 70 centimeters. And you all know the formula. 300 divided by the frequency in megahertz gives you the wavelength in meters. In this case, it's less than a meter, 0.7 meters, 0.69 something. So, and I also have some equipment that works at 432 megahertz. It's a transverter and a little 10 meter, 28 megahertz radio that feeds into it that gets converted to 432. So I'm putting a signal out on this antenna at 432 megahertz. This is my source antenna. So we can do things. All right, I always start out the talk for the benefits of the newcomers with a basic idea that's very important. And if you look at any of the study guides for the general or extra, they talk about this antenna. Only I'm going to do it with a light bulb. It's called an isotropic radiator. Anybody know what that is? You all should know what it is, unless you slept through the last talk. What is this?
Vertical.
No, it isn't vertical now. What do we mean by isotropic?
Same in all directions.
All right, it radiates equally in all directions like a sphere. I could walk all the way around this thing, say a foot away, and I'd get dosed with an equal amount of energy. There's no one area that's got a stronger amount of energy than any other area. This is a sort of a reference idea, but it's a theoretical one because you can't really make a very perfect isotropic radiator in the real world. Why not? Why isn't this equally radiating in all directions?
Ground.
The ground. I'm standing on the ground. So half my signal is lost in the earth. That's a good point. And what else from a practical standpoint? Go all the way around it. Is it radiating there?
No.
I got a blind spot. The stem, the wiring to the outside world, blocks at least a little bit of it. It's kind of like the optic nerve in back of your eye. Your eye can't see back there, but the nerve's in the way. So it's sort of a utopian idea. The only way one of these would exist is in outer space, where the Earth isn't there. The sun is a pretty good example. But you've heard about the solar storm. Even that's not perfect. There might be sunspots that make it put out more energy in one angle than another. So even the stars are not perfect isotropic radiators, but they're a lot better than this. So in the ham world, I don't like to think of it as a hobby. You know, I hear that word hobby. It's a lifestyle. It's not a hobby, all right? Or it's part of a lifestyle anyways. Most of us want to talk to our friends. We don't care about talking to the man on the moon or the earthworms in the ground. We want to radiate a signal in some directions. So if I could take this energy, instead of wasting it up there and down there, and sort of redistribute it so that I could talk to somebody I want to, I could use less power. I'd be less wasteful, wouldn't I? So for the most part, we want something that's better than an isotropic radiator, at least in some direction. But there's a rule in life: you can't get something for nothing. So if you try to, you'll find it doesn't work. So in order to get energy in his direction in an increase, I have to take it away from somebody else. I've only got so much money to go around, so I can distribute it equally, or I can give more to one person that's deserving and less to another. But I'm going to put more energy in him and less somewhere else. How do I do that with this light bulb?
Point it.
Point it. If it's isotropic, it won't matter what I do. How do I make an isotropic antenna into something that has a quality we call gain, or an increase?
Reflector.
I can put a reflector on it. And that's what the mag light does. So now mag lights are up, or passe, I guess, because everybody's got LEDs. So I can take the same amount of power and increase it in one direction, but I have to give it up somewhere else. So if I'm talking to a group of friends, I might want to spread it around the horizon and not put it up there and down there. It's sort of like a pancake that you step on. And the more you step on it, the more batter goes out this way and the less that way. I can change the amount of energy by changing the focus of it. So if I have an antenna with a rotator and it's got a lot of gain, in other words increase over the isotropic radiator, I might have to point more sharply, and I'll have fewer people within the beam. All right, we call that a beam. Think of a flashlight beam. So a lot of antennas that hams use are called beam antennas. They may be Yagi antennas, but they may be something else. And all of these classic antennas start out with a few simple ideas and add to them in very clever ways to make them have more gain. Hams like gain. Hams also like gain in a small space. They might want a giant antenna, but they don't have the room for it. So you have to compromise in life. We can't all have a rhombic in the backyard, and we can't. A lot of us can't have a lot of things. So we have to put up with some things. And if you live in a covenant place, you might have to come up with some ideas to fit your situation, which may be different from mine. So we can't see radio waves. We can see the effects of light, but they're very similar. Light waves and radio waves are similar. You remember from last time? How are they similar?
Speed of light.
They travel at the speed of light, which is, well, how much is it?
186,000
thousand what?
feet per second.
Miles per second.
Miles per
No, too slow. Miles per second. That means it can go around the world in 1/7 of a second. It can go to the moon and back, which is a 500,000-mile round trip, in about 2.5 seconds. And if you've never done moon bounce or EME, it's pretty exciting to hear your own echo come back, delayed by 2.5 seconds. If you send Morse code, you'll catch the tail end of it. And you can work anybody that way by using the moon as a reflector. And then you notice the speed of light. But on Earth, for the most part, it's fast enough that we don't sense the delay between you and your friend, across town. Sound waves or vibrations in the atmosphere, they only go around 1,000 feet per second, so they're much slower. And light and radio waves have that in common. They're both electromagnetic waves, and they travel through space. They don't need the air like sound does. If you took the air out of this room when you spoke, you probably wouldn't hear each other. You might feel the vibrations on the table. But radio waves can go through space, which is sort of neat. It's how you can work satellites and how they can, how telescopes, radio telescopes or optical telescopes can pick up signals from millions of light years away. A light year being the distance that light travels in 1 year, which is what, about 6 trillion miles? Pretty amazing. And it's amazing how weak a radio signal can be detected at great distances. That's one of the things about ham radio that's always been exciting. And a true ham will always marvel at the ability that he or she has to send a signal to their friend by these magical invisible waves. And 100 years ago you probably would have been jailed for playing around with black magic, but now this stuff's all around us. And unfortunately, the people that aren't in this room are using their cell phones, and they don't, for the most part, have a clue that they're using magical radio waves. They've taken it for granted. And as hams, we don't want to take it for granted. We want to use it and learn about it. But most people, the technology is so advanced that they just use the thing and take it for granted. Things that would have been magic in the past, are now commonplace. Who knows what the future is going to be? But pretty interesting. All right, well, instead of using a mag light and sending off a light beam, I'm going to do pretty much the same thing with this little beam antenna. And right now it's shooting a signal in that direction. As soon as I put some power to it, there it goes. Couple of warts. I hope that's good. And the energy is going off that way. So I'm going to just get a dipole, 2 poles. The dipoles are half wavelength long. As I devote a good part of the first page in the handout to dipoles, because they're a very basic antenna that just about any ham can build. Notice I said just about. I think everybody should try to build something like this, whether it be HF or VHF, and the length determines the wavelength. It's a half wavelength long. It's not a full wavelength long, it's a half wavelength long. What happens is the radio wave is alternating back and forth. You put electricity into this antenna at 432 million cycles per second. So it's changing at twice that rate. There's 432 million cycles, but a cycle has both going that way and that way. So a cycle has 2 changes or 2 alternations. So the electrons are rushing here and rushing back, rushing here, rushing back. And it'll cause a certain amount of energy to get propagated into space. But what's neat is you can use a similar antenna or another type of antenna and pick up the signal and convert the radio waves back to electricity. Because it's weaker than you start with because it's spread out. So you're only catching a small dose of what's sent out. So the electrons during half of the cycle are going one way, and then they're turning around and going the other way. And if the length is exactly right, they'll be timed so that they stop and kind of go back and forth. They're like marching up and down a road and then backtracking, and you have so many minutes to do this. So you've got to time yourself to do it. So the time that it takes is determined by how long the antenna is and what the frequency is, the frequency number of cycles per second. So it's a half wavelength long, but don't forget during a cycle it's traveling a full wavelength. It's going half wave and then back. So one half of the cycle the current's going one way, the other half the current's going the other way. Now in my drawings I have little arrows. On all the drawings, my goal here is to help you to understand, I hope you understand how these antennas work so that you can look at them and analyze them and figure out how it actually works. And so I'll give you a few rules. I show the arrows in one direction only referring during part of the cycle, because if I could draw another picture with the arrows going the other way. But it's relative to each other at the same time what the arrows are doing. I snapshot an instant in time and say the current's going that way. In another part of the antenna it might be going another way. All right? So I'm going to convert my radio wave back to electricity, and make it do some useful work, which is, instead of running a radio, lighting up a little light bulb. All right? Pretty neat, huh? Now, somebody looked at this and said, where are the wires? How did you do that? There's no wires connected. Right? Well, if you don't believe in radio energy around us right now, if this doesn't convince you that there's some sort of energy coming off here, then I don't know what I can do. Mickey, you want to be the holder of the light for a minute? Yeah. I learned not to let the audience do this because I blow them out. They're easily blown. They're little 1.5 volt 60 milliamp. They're like 60 milliamp lamps. So we're talking like 100 milliwatts. I'm starting out with a few watts. Most of that energy is spread around the room like in a cone. So she's only intercepting a small part of that, like a slice or a little. It's like cutting a little circle out of an orange or something. All right, now. My antenna, think of this antenna like a mag light, right? It's like a cone of energy coming out. I'm going to move it so that she gets it weaker. You want to get a little bit brighter. That's good. Hold it up. There we go. Now watch what happens when I turn it. Now, here's something that's important if you're upgrading your license. There's a term called beam width. And you hold it right there. Go up so it's, well, there you go. The beam width is the number of degrees between the 2 points where the signal drops to half. There's one. I'm doing this roughly. There's the other. Out of 360 degrees, we're talking maybe 35, 40 degrees or something between those 2 points. Those are called the half power points. Now, if you're really doing this accurately, you would use some sort of a calibrated meter. A light bulb, it's pretty hard by eye to guess that the power is dropped half. Plus the light bulb changes resistance with power, so it's not even that accurate. But it gives you an idea what's going on. That's the horizontal beam width, or the azimuth. You'll see that word azimuth? That's along the horizon. There's also vertical beam width. All right? Usually a little bit broader. In other words, the angle is a little bit greater. They may or may not be the same. In other words, it may not be a cone, it might be like an elliptical cone. So it might be a little broader this way than that way. So that's the vertical or elevation beam width. Why is that important to know? Because when you're aiming up at your satellite, you got to know that the satellite's within that beam or you'll lose it fast. You know, once you get out of that half power point, it really drops off. So, you know, you're illuminating like this big cone in space. You've got to be within the cone to pick it up. Now, you can make it sharper by adding more of these elements. That focuses it more. These elements like a lens, you know, they just kind of focus the beam. They actually bend the wave front by slowing down the middle so that it converges upon the source. It makes the cone smaller, but the thing you gain from that is gain. The signal's stronger, it's just that you have to point it more accurately. So the bigger the beam antenna, the more gain you can get out of it. I have an antenna, I have two antennas like that at my house up on a 100-foot tower with, they're 25 elements each. That's about, how long is it, 18 feet? 17 or 18 feet long, each one of the and they're both stacked together to give me more gain. That's up at 100 feet. I can regularly work my friend K1RZ in Maryland on 432 megahertz. You know, most people think of these frequencies as local. Well, for me, that's kind of like the limit of local. And, you know, so really, he's got a good station. And I have a pretty good station. So. And I can do something similar. On 2 meters, it's even easier to do. All right, so that's beam width. All right, so you can see the compromise you have. If you want more gain, you've got to narrow the beam width because you're putting more energy in one direction and less other places. But you end up with a bigger antenna, more problems. You need a better rotator. You don't want one of these TV rotators that says north, south, east, west, and that's it. You might have to point to within a few degrees of being correct, you know. And when you do moon bounce, it's even more so because you might even have a bigger antenna. All right, so there's your beam width, your gain. Any questions so far? We've already covered most of this stuff. So I'm going to get into a few things on dipoles because they're kind of like the building block of just about any of these antennas. Well, let's see, Mickey, we don't, you can, yeah, or I'll put it over here. There are all kinds of offshoots of dipoles. Oh, I know what I'll do while I get you here. How critical is the length of that antenna? Watch, I'm going to detune it. Get it so they can see it. Okay. I'm going to detune it. I'm going to put just a quarter wave piece of wire. I'm going to change the length of it. I kill it. Notice that I don't kill it here in the middle, but I kill it at the ends. Isn't that interesting? If a bird lands on the end of your dipole, it's worse for you and the bird than it is in the middle. It's worse for the bird because there's very high voltage on the ends. The current goes to zero. It's an open end. So the current diminishes to zero and the voltage can get very high, and you look at the first picture, you see that. But in the middle, the current is high and the voltage is low. So I don't detune it as much as I do on the ends. And you'll see in the diagram, I show a picture on the very top on page 1 of the current and voltage. Notice the current maximizes in the middle and the voltage is equal and opposite at the ends, like a seesaw. When one end's positive, the other is negative, and during the next half of the cycle they change positions. Everybody follow that? And the current arrows, which I didn't show on the first picture, will also reverse direction. So that's your basic dipole. If you're transmitting in a dipole, do not stick your tongue on the end. In fact, even with a few watts, it can be very dangerous. There's quite a shock from that. I can light up neon lights and all sorts of things on the ends. It take over 100 volts to run them. So I can also detune, let's just get it so they can see it better. I can also detune this antenna. See that? Remember that during the snowstorm, because snow changes the element size, and it's not, well, it isn't a perfect conductor, but it loads the antenna and detunes it. So you'll often find that in a snowstorm, your 432 megahertz Yagi may not work very well at all. In fact, it may even work backwards. And 2-meter antennas, if they don't work, just wait till the snow melts, which around here could be a very long time. All right? All right, so any questions on that? All right, now, always think of these UHF antennas in your situation. You might want to build a dipole for 80 meters or 40 meters. And you don't have 126 feet or 130 feet to put up an 80-meter dipole. Well, what can you do? The easiest thing to do is to bend it. You can get away with this because the high current is in the middle and the low current's at the end. The radiation from this antenna is mostly from the high current part. So as long as the antenna is the right length, you can bend the ends down and you don't lose much. There's a point, if you try to make it that long and almost droop down totally vertically like this, you're going to lose most of your stuff. So you're going to have some current there. So that high peak in the current you want to radiate. So you might have a couple trees that are 100 feet apart, and you could just hang these ends down. But be careful with the end hanging down near the ground that you don't zap your neighbor, unless you want your neighbor to get zapped, all right? Which might be a neighbor that doesn't like antennas, you know. All right. Now I've got a bigger light bulb, so it's not going to be as bright. This is going to light, yeah, there it is. So I have to have more energy. There it goes. I have to have a little more energy to make this one go. Or I can turn the power up some. I think I'll do that. Get a couple more watts out of it. This is a number 49 lamp, so this takes more power than the little one. All right, so that's my bent dipole. I can detune it, see? I don't detune it here, but as I go further out, I do. By the way, the impedance, the number of ohms that you see for this dipole varies from about 72 ohms in the middle, and if you split it somewhere off to the side, it goes up because impedance depends on voltage and current. So the voltage is going up towards the end and the current is going down. So when you divide one number by a smaller number, you get a bigger number. So the impedance goes up. So at the end, it might be thousands of ohms. The middle might be 70 ohms, and somewhere here might be whatever you want in between those two extremes. So you can feed a dipole off center. I'm saying that because it's a popular thing to do nowadays for certain reasons. All right, so you can bend the antenna. It's a good thing. You can also shorten it by loading coils. Here's a loading coil. couple of them. And on these frequencies, they're self-supporting, right? And there's a little capacity hats on the end. They physically shorten it. And let's see if it works. Oh yeah, look at that. Now, when you do mobile work, you probably can't get on 80 meters with a full-sized antenna because, first of all, you'd probably get arrested for driving under an overpass and knocking the cement down. It's not, you haven't got enough room on your car. You have to shrink it a lot. So your antenna might mostly be loading coil. On 2 meters, those so-called rubber duck antennas, they're miniature versions. They're mostly coil. Some of them get hot, by the way, which tells you they're not very efficient. The downside of this, you lose power in the coils from heat, and the bandwidth narrows. The bandwidth is the frequency range over which it works. In other words, the shorter you make it, the narrower the range of frequencies you can use it over. So there's a downside. If everything didn't have a downside, we'd be all doing the same thing. There's got to be some benefit, but whenever you see a benefit, ask what's the downside, because there might be one. You may be willing to put up with the frequency narrowness by maybe retuning it, because to you it may be more important to have a small antenna you can fit in your yard. For me, it's more important to have an antenna that works and not worry about the size. It's a different set of expectations, you know. All right, so I can shrink it down. I could even go so far as to make a dipole look like this. You might say, what kind of a dipole is that? I really shortened it. And I put end loading on it. So, all right, if you looked at that, you might think,
Lazy H.
what's an H? What's the polarization of this, by the way? I didn't even get into
Both?
polarization. I didn't get into that, did I?
Vertical.
Is vertically polarized? Everybody agree?
Horizontal.
Horizontal. This is the dipole. These are just end loading capacitors. And they're both equal and opposite. So the arrows for the current are dividing. The current's dividing on each end into two paths. They're both working against each other, so they don't radiate. So if the current in the middle is going this way, it's going to go up this way and down that way. It's kind of like a road that diverges into two 90-degree branches. And likewise, the arrows are going in. So these two parts cancel out, and all you got is the radiation from that. But it's shorter. This might be the kind of antenna you might put up if you had two skyscrapers near each other. You got a lot of vertical room, and you don't have much horizontal room. You can sort of swing them between, if you can picture that scenario. Let's see if I'm true, if I'm right. Of course I am. I wouldn't have said it if I wasn't. There we go. All right, that's horizontally polarized. And by the way, I didn't mention it, but polarization of radio waves is the electric part of the electromagnetic wave. There's an electric part, which in this case is horizontal. It's going kind of like this, like a sidewinder rattlesnake. And the magnetic part in the electromagnetic wave is going up and down vertically. And they're both at right angles to each other. So when the electric part is parallel to the Earth, which makes it horizontal, then you have horizontal polarization. If I want vertical polarization, I can just turn that around and now, see, now I'm vertically polarized. Which kind do you use? Depends what the other guy's using, right? Well, what do we use? What do you guys in Keene area use for polarization?
Depends on what mode.
Depends on what you're doing, right?
Right.
Why is that? Why does one mode favor one and not the other? Part of it's convention, been done that way for years, but part of it is that in some cases vertically polarized antennas are easier, say, to put on your car. So for mobile use, vertically polarized antennas are easier to deal with, and that's why the FM people tended to use that over the years. But technically, they could have used horizontal if they could build the antenna. It's just harder to make. And most DX people, because of the height above Earth and other factors, find horizontal better. So, but either one will work. And you'll find that on HF, through the ionosphere, the polarization gets twisted and tumbled around anyways. So just wait it out. If you got, I do a lot of stuff with vertical polarization on 40 and 160 meters, and I work all kinds of stuff. And I don't know what the guy at the other end has, but I know the signals fade, so, you know, I just wait and it might pick it up. On VHF, I use mostly horizontal because it tends to stay the same. There's no ionosphere, you know, to mess it up. So that's polarization, and you know, that light bulb that Mickey was playing with here, Same thing. There's horizontal and that's vertical. When they're cross-polarized, you don't get anything. The books say 20 dB down. In reality, there's a perfect null. Only if you are in space and there's no objects in the way. When you have trees and stuff, it kind of jumbles it a little bit. So that's probably where that figure came from. So for FM, use vertical. And for single sideband, by convention, use horizontal. So what does that mean? It means you've got to convince your family that you need 2 antennas, not just one. Right? You always should do that. Set up a demo like this for your spouse and say, this is why I have to have 2 antennas. And some people are pretty clever. In fact, somebody was talking about this the other day. They said, I'm going to do both. I'm going to turn my antenna 45 degrees. Well, that's fine if the other guy or gal turns their antenna 45 degrees. But what if there's 3 people? So one person's like this, and you're like that, and the third person's either going to be this way or that way. It means that 2 out of the 3 can talk. Think about it. So that's a smart idea if everybody doesn't get on the bandwagon. Now, if you want to do both, and you go horizontal, you lose 3 dB, or half your signal, by being 45 degrees off. So sure, I'm going to get a signal this way and a signal that way, but it's going to be down 3 dB. It's sort of like cutting your beam antenna physically in half. 3 dB. Half your power is being lost in the unwanted polarization when you're 45 degrees off. But when you're 90 degrees off, it's a null. So there's your answer. So you'll hear, I heard people discuss this. I didn't want to get involved in discussion because I didn't have enough time, to explain that. Yeah.
You also can't put the vertical Yagi on a metal pole.
That's another thing. He's got a very good point. The metal pole, by the way, some people have the idea of putting it like this, and then they put the metal pole right up through, and they put like a horizontal Yagi on top. The problem with that is these elements are blocked. So some of the energy starts squeezing out the sides. So instead of a nice cone of energy, or major lobe as we call it, it's got a bunch of minor eruptions off to the side of energy that you don't want being reflected off that pole. And depending on how long the pole is, you're going to have RF going up and down here. The compromise I'm doing here is to just end halfway up. So at least half the element's clear. But don't run it all the way up through. And somebody might say, well, I'll use a fiberglass pole. That's fine and good, except they've got what? Cable. And if you have another antenna on the top, you got another cable. Well, those cables act like poles, and they pick up energy. And it'll probably radiate down into the shack. And you know that because you can look at the SWR, and if you see it move, the reflected power goes up and down when you put your hand on the cable. It means it's probably the outside of the cable is actually picking up energy from the element. So always think about that when you feed an antenna, to keep the coax at right angles to the element so it doesn't pick up a signal parallel to it. And there are ways around it. One is to do what I just did here, is to put a ferrite bead. That'll help to choke off some of the energy. If you want to get really good, put a couple of them a quarter wave apart, and that'll get most of it out of there, except it's wasting energy and heat, but it's there. So that's a good point you made about that practical side. What do I do at home? I have 2 vertically polarized Yagis side by each on a horizontal boom with a tower in the middle. So each one is offset from the tower so it doesn't block it too much, and they're phased together to give me extra gain. The beam width gets narrower when you do that, but that's one way around. The other way is to end mount it. In other words, mount the pole behind the reflector where there isn't much energy, but you can't do that with long antennas unless you have a lot of braces or something, or ropes or something to hold it up. It becomes mechanically unwieldy to do that, but that's a trick. All right, that's a good point. All right, where are we? Dipoles. All right, I'm going to go just a little bit more because dipoles, as interesting as they are building blocks. And here's another dipole which goes back a long time. It turns out it goes back before World War I, as I found out recently in my 1925 QST, when somebody mentioned that this idea came out before the late war. So the late war would have been World War I. It's an end-fed dipole. Here's the dipole. it's at this wavelength, the 70 centimeter band, a half wavelength, is about 12.5 inches long. 12.5, 13 inches. That's a dipole. How many ohms is it at the end? It's maybe 70 ohms in the middle, but at the ends, how many is it? Lots, right? Could be thousands of ohms. Could be a real lot. Very high voltage. So what they did in the early days, they were experimenting with airships. The Germans were making these dirigibles called Zeppelins. And they would hang a dipole. And you can remember a dipole in those days was very, very long because they didn't know how to make short waves. Their waves were in the hundreds of meters long. So we're talking about a dipole that might have been 1,000 feet long or something, hanging from this dirigible. It'll be hanging down below it. And the high voltage end was suspended below the dirigible by this matching stub, which is a quarter wave long. This matching stub looks like a short at one end, but a quarter wave away between the two ends is a very high impedance, virtually open. Somewhere between 0 and high is whatever you want. It could be 50 ohms, or which they didn't use in those days, but all radios today seem to. Or it could be 600 ohms. You'd make 600 ohms just by sliding it further down. Somewhere between 0 and thousands of ohms is any practical thing you want to match it to. So your transmitter goes here. I've got a light bulb connected. In fact, it's an LED with a little diode power supply, because LEDs don't work at 432 megahertz. So you make DC out of it to run it. This is called a ZEP, Z-E-P-P, named after the Zeppelin. Has another smart thing about it. What was the dirigible filled with?
Helium.
Helium.
Hydrogen.
No,
Before they got smart, they put hydrogen. What happens when you have a high voltage antenna inside or near the big gas bag with hydrogen in it? Boom! So this keeps that high voltage point away from the dirigible. It might be 300 feet from here to here and another 600 from there to there or something. So in other words, it kept it away. So that was one safety thing. Well, that Zeppelin antenna is now popular among hams, except most hams don't realize it's the very same antenna, except we call it a J-pole because it looks like the letter J. So the bottom part of the J is the matching part, and this part from here on is a half-wave dipole. It's really a dipole end-fed. What's the advantage of end-feeding a dipole? The coax, when it's vertically polarized, doesn't hang down alongside half of the antenna. It's below it. So it doesn't interfere with it. That's one real advantage. You can hang this thing from a tree and put your coax right here and go down to the real world and not have to worry about, you know, coupling RF energy and so on. They're not quite as easy to match as a dipole. I'm going to make it leave it horizontal, although most hams use it vertically. Let's see, there it goes. There's the LED. Pretty neat, huh? I can actually run an LED over a long way. So it's vertically polarized. I can detune it at the high voltage point on the ends here. So bright that it's still, all right, there we go. But not in the middle. So the middle is there's sort of a neutral point where the current is high and the voltage is 0. And if you were going to ground this thing to a tower, you could do that. Use a quarter wave piece of tubing and ground it right there and hang it off of a tower. That's a neutral point and it'll still work. All right, so the hams on 2 meters and so on, or 70 centimeters, tend to use it like this. There's your J. Now, in this plane, called the azimuth plane, it's omnidirectional. See that? That's the horizon. But overhead, nothing. Or down where the earthworms are, nothing. So here and here, there's a big null. It's like a donut pattern with a null here and a null there. That's the hole in the donut. If you looked at it like a contour graph called a polar plot, you will see that. So the energy is concentrated on the horizon. And it's pretty broad. See that? I could be quite a few degrees above or below the horizon. Now I'm down tilting. Picture this like vertically polarized and I'm tilting the whole room or this way. Rather than tilt that antenna up or down, it's easier to do this. Everything's relative. If you can picture that. So that's an omnidirectional. It's not unidirectional. It's omni, it means all directions, but only on the horizon sense. The isotropic was omnidirectional in every direction, up, down, everywhere, it's the same. But this way you get gain. So this has gain over isotropic because I'm taking energy that would normally hit the ends and I'm making it more where I need it, which is the horizon. This is like the pancake you step on and you spread it out this way, make it thinner. So that's my end-fed dipole. I could use a regular dipole the same way, as long as the coax was coming off of it to your radio, because most of us have a radio not at the antenna, but in a building or something, and you want cable going to it. It's a whole other talk, by the way, is transmission lines. I think we did that, didn't we?
Yeah.
Yeah, and how the signal gets to the radio and vice versa. All right, any questions on these dipoles? All right, I'm going to extend the dipole. I'm going to do some things to it. But before I do things to it, I'm going to show you, with Mickey's help, three different types of antennas that we're going to get into. We're going to combine dipoles. So Mickey's going to be the holder of the power combiner. We did it. I think we did it in one of these talks, but I'm going to do it again because this is an important thing to remember. I need my little light bulb here. We're going to take the signal from two dipoles and try to combine them to get more signal, because I'm going to capture more energy in the room than I could with one dipole. Each dipole can only pick up so much energy based on its capture area. So I'm going to put one dipole on one thing and one on the other. And these are two equal lengths of cable. I think I did this last time, or something like it, but I'm going to refresh your memory, maybe. Notice the color code on the dipoles. Green and red. If you're colorblind, you're in trouble. Now, let's see if we can make this light up so that everybody can see it. I'm going to put these things one above the other. And I notice I'm matching the green on one end and the red on the other. Let's see if I can get it. Is it lighting up?
Oh yeah, it's lighting up.
Lighting up. All right, notice that if I go too close or too far, I lose it. These things are territorial. They like their space. If you put them too close together, they rob power from each other, because each one has a kind of an ellipse around it of energy that it's capturing. And one of the ellipses is going to interact with the other one if you put them too close. And if you put them too far, you're out of the beam of the source antenna, which you don't want either. But it turns out that that distance is a little over a half wavelength. It's about 5/8 of a wavelength where they're optimized. So if you're going to stack dipoles, you should, in theory, get twice as much signal with two of them as you do with one. Now this is called a broadside array. An array is a group. So we got two dipoles, it's an array. It's a simple array, and they are in phase with each other. Now notice the phase diagram there? That means the signals on the different parts of the cycle are in step with from each dipole. Why? Because two reasons. The distance from the source is the same. If you could measure the distance from this dipole to the source and that one, they'd be the same. Plus, the distance it has to travel in the cable is the same because the cables are equal. So that means they arrive in step with each other and add. Like, think of people marching. The odd person that doesn't march in step with the others is out of phase, as we would say. Right, so it's called a broadside array because the wavefront from the radio source is perpendicular to or broadside to the plane of the elements. Where's the plane of the elements? Here's the two elements. Where's the plane of the elements? Can you picture it? It's a sheet of paper down through both of them, right? That's the plane of the elements right here. So perpendicular to it means it's coming out that way. Broadside. It's like hitting the broadside of a barn, right? This is the plane of the elements right here. Right? So if you could picture that easel transported over there, the signal's arriving, so all points on that wavefront are hitting that plane equally, and they're arriving. So that's called a broadside array. Now, what happens if they're out of phase with each other? I can do that by turning one of the dipoles, the red having the center of the coax cable and the green having the shield. I can turn one around so that red and green aren't in the same line, and see what happens. Goes away. What happens to the energy? It now shifts. See that? Instead of picking up broadside to it, I'm now picking it up in the plane of the elements rather than perpendicular to the plane. This is called an end fire array. End fire meaning the signal is parallel to the plane containing the elements, which is this. So all I got to do is turn one of the two antennas around, and I can make a broadside antenna, which is this one, into an end fire antenna, which now is turned 90 degrees. Now this should give you a clever idea. You could make a pair of antennas for some band, like 40 meters or something, where they're big, and steer the beam by flipping the phase of one of the two. And you can steer it that way or that way. It's bidirectional, by the way. What do you mean by bidirectional? Am I putting somebody to sleep?
Oh, you're right.
Put the follow me around? Yeah. All right. Well, oh, this is a backwards. Bidirectional means it can go this way and this way, right? Or broadside, end fire wise, it can go this way or this way. So that means this antenna works for California and Europe, not to South America. This way it might work to South America and not Europe or California. South America and the Arctic. So it's a bidirectional, two-direction antenna. Everybody got the idea? Broadside and end fire. It has to do with phasing. By the way, in an end fire array, you can mount the antenna's elements much closer together, this way, all right? And the gain will go up at very close spacings. Remember the broadside one? They wanted to be about 5/8 of a wave apart. Right, there we go. Whereas this one, they're much closer. But there's a price you pay for it. The frequency range over which that works is very narrow when you start doing that. There's a third way of doing it, and it's called collinear, which means end to end. All right, if I throw one out of phase, nothing. So collinear means end to end, and it's in either broadside or end fire, because there is no plane of the two elements. They're end to end. So those are three configurations. All of these antennas are configurations using one or more of these ideas. I want to show you a couple of basic dipoles. I want to dig out the top secret antenna. You've seen this, some of you have seen one of these, but not all of you, I don't think. So I just brought one of them to show you, and see if we can light it up. Yeah. So, yeah, there it goes. This is a, what do we call this? A dilly dipole, also known as a dipickle. Right. And maybe somebody can explain why pickles give off green light. But anyways, these actually work pretty well. It's vinegar-based technology, and they're very conductive. This might not be a classic antenna, but it's a Vlasic antenna. In fact, I made, this is a whole nother part. I've actually made several versions of pickle antennas. I made one of those little ones with loading coils, with loaded gherkins. They had little tiny gherkin things with loading coils, and that worked pretty well. And I made a Q pickle quad and several other things. But anyways, we've actually made two-way contacts from my house to K1WHS in Maine. He built something similar, and it was almost as good as a real wire dipole. I mean, they're very efficient. I ran like 90 watts into one of these things to see how hot it would get, and it ran pretty well. The SWR didn't change much, and it didn't get very hot. Ran cool as a cucumber, and it was kind of neat. So, anyways, you can make antennas out of all kinds of conductive things, but at this frequency, that's pretty close to a half wavelength. long. It's not quite that, but it's close. Because it has electrons tend to flow on the outside surface. I've also made hotdog antennas, but the hot dogs I had for the last 4 years was turning green, and we threw them out. You know, I should have saved them for St. Patrick's Day. Green. I think we were looking for them. We couldn't find them. We didn't have time to buy any, but maybe I'll have them at the flea market, the hot dog antennas. But they're not quite as good, but they're pretty good. They're pretty good. So, you know, it's fun to play with this stuff and learn from it. You might laugh at the pickle idea, but a few years ago when Arecibo Dish in Puerto Rico was on with their 1,000-foot dish, I received their signal loud enough to run a loudspeaker bounce off the moon with this antenna and a preamp on it.
Pickles.
It's 2 pickles, probably the same ones here, in fact. And it was amazing how loud it was, you know. So they thought that was kind of neat. I didn't transmit into it, but I did work them, and so did Mickey. So anyways, I have a picture of that if you want to see it. So you can do all kinds of fun things and so on. Well, while I'm on the dipole idea, it's possible to take 2 dipoles and cross them and put a phasing cable between them so that you have what's called circular polarization. And that allows you to work satellites, because the satellite's tumbling in space. And the advantage of circular polarization is that when you go around, you don't lose it, see? All right, now you can it also at the same time, besides having that corkscrew circular polarization, has horizontal polarization in this sense. You used to see these in the 1950s and 60s on the roofs of cars on 2 meters. It's called a turnstile. And on 2 meters, it's 3 times the size. It's like 38 or 40 inches from here to here on 2 meters. But put on your car. That way you can go around the corner and you don't lose people like you would with a regular dipole. So it is possible to make a horizontally polarized antenna for mobile use. It's just a little bit trickier. But this type of antenna is very good for working satellites. And sometimes you'll see 2 of these beam antennas with elements crisscrossed, fed the same way with a 90-degree quarter wave piece of cable between the 2 sections, you know, to give you that polarization. So that's a special thing you can do with dipoles. All right, any questions on dipoles while we... All right, well here's another one. This is, half of the dipole is really these 4 radials, and this is the other half. So this is called a ground plane, because instead of having 4 radials, there's often a sheet of metal or the roof of a car which acts like a plane of metal. When you have them sticking out this way, instead of 72 ohms, it looks more like 36. And when you have them going down that way, it looks like 72. Somewhere between those 2 extremes is the 50 ohm point. Another question on your exam: what's the purpose of drooping the radials? It's mostly to match it to 50 ohms for your radio, which is probably 50 ohms. And by the way, when you do that, the frequency changes slightly, so you have to change the length of the things to make up for it. So most people that use ground planes use them like this, and they are vertically polarized in that sense, but also omnidirectional, much like that J-pole was. This is a very unforgiving antenna, meaning that you can build it and be pretty sure that it works. I should say very forgiving antenna, not unforgiving. And it's pretty hard to make a mistake with this antenna. You know, it works very well, and even if it doesn't work perfectly, just bend the radials up or down, and you'll probably find the SWR is very, very low. May not be 1.0, but it'll be close to it. So CBers use this a lot. 11-meter band, where this is about, how long is it? About 8 feet from here to here, so 8 or 9 feet. And 8 feet from there. So you see these on the roofs of houses more in the past than now, but it's a basic dipole. And on the low frequencies, like 160 meters, these radials often become buried wires like spokes of a wheel in the ground, and this is a quarter wave thing. So the missing half of the antenna is in the ground, or a replica of the ground, which is what this imitates. What kind of voltage do you have here? Here, 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 and here. Kind of voltage. Putting everybody to sleep. Pretty high, right? very high. So you could hurt somebody if you have it accessible. All right, dipoles. Remember the ZEP antenna? There's one dipole fed at the end. Suppose I took two of those dipoles and fed them at the end like this. This isn't the right one. It's is it over here? No, it's right here. This is it. Very high voltage and very high impedance here and here. But now I'm going to feed two of them, and this is a phase reversing stub that puts these two things so that the ends, this is plus, minus, plus, minus. So these two are opposite polarity at the same time, but the dipoles are in phase because the two pluses are here and the two minuses are there, and on the next half of the cycle it's reversed. What do you think this is called? If this thing, this J-pole is called a ZEP antenna, and I bend one of them over and add a second one, what do you think I call it?
Double ZEP.
A double ZEP, aha! You've been reading your antenna book. All right, now this is something that you'll see, I think even MFJ is making one of these. I'm going to put a little wooden holder on it. This end is 0 ohms. That's a short. I can touch that and not get hurt, but don't take my word for it. And here's it's pretty high voltage here. And this quarter wave transforms it. At some point, you can match it to your 50 ohm radio or 200 ohm radio, whatever you want. Let's see if it works. Oh yeah. Now, this is a what kind? Remember the 3 kinds of antennas that we spent some time on while you were asleep? Which kind is this?
Horizontal.
Well, it's horizontal, but the three categories where Mickey was getting entangled with the wires there, and we had broadside. What are the other two? Endfire and collinear. Now, which one is this?
Collinear.
Collinear, end to end, right? You can't say it's broadside because you don't have a plane that contains the two elements that's defined. The planes, there's an infinite number of planes that both elements go through. But it's going to have some gain over one dipole because the beam width narrows as opposed to one. Now it's be sharper to you. So it's a sharper antenna than the plain dipole is. It doesn't quite have 3 dB of gain. And the reason is that the antenna ends are too close together. Remember those little apertures surrounding the antenna? They intersect each other, so you don't, one robs power from the other because they're too close. So you don't get 3 dB gain, you probably get less than 2. But still better than nothing. However, it is sharper this way, so that means the null on the end is going to cover a bigger space. So if you're going to build one of these, you're going to have enough room. You need twice as much room. And you also have to remember that you're going to lose more signal here and you're going to gain more there. So if you're willing to, if you want a dB and a half or 2 dB again, this is a simple antenna to make if you got a matching. I think MFJ makes one with twin lead stubs and so on. So that's called a double ZEP. All right, I'm going to go even further. How do I increase the gain of these two dipoles if they're too close together? Well, spread them apart, right? Well, that's kind of hard to do with this configuration. But it turns out that most of the radiation is in the middle where the high current is, but not at the high voltage ends. So if I extend the length of this wire to beyond the half wavelength, I should be able to pick up some gain. We'll see. And that's called a EDZ, which means extended double ZEP. Now, see the little black pieces of tape here? This is the half wave dipole up to here. This is the extension that I added here and here. So I've made it longer. In fact, it's about 5/8 of a wave long now. And let's see if it works. Oh yeah. But it is sharper. It's sharper in tuning than the other one. So I've gained an increase because I've separated the antennas so they can get more of their 3 dB gain. However, this part and that part are out of phase with each other. They don't lose much signal because there's not much current there, but they are out of phase. And if you look at the picture, wherever it is, of the extended double ZEP, I don't know what page it's on. First page? Anybody find it here? Oh, it's under collinear arrays. All right, you'll see that the little arrows in the middle of the antenna, that little eighth wave segment, they're going backwards from the other. It turns out every half wavelength of a wire antenna, the current reverses. So those are out of phase, so they rob power from the fact that I increased. So if you kept doing this and lengthening it to separate them further, the gain that you get increased becomes more lost by that out of phase current. So there's a point of diminishing returns. So if you get much further apart, then you start to lose energy, and that energy becomes unwanted side lobes or energy in other directions. So there's a limit. So this is about as far as you want to go with this antenna. But I believe I think MFJ even makes an extended double ZEP. This has pretty close to the full 3 dB of gain over the regular double ZEP, but it's longer. And somebody came up with a clever way of actually eliminating these sections which have inductive reactance and putting a capacitor in series to cancel out so it would match well, because this is not a 50 ohm, or it's like several hundred ohms with reactance built in. So you cancel out the reactance with capacitors and it looks like a resistive load, and you need a 6-to-1 balun or something to match the thing. So if you're willing to do all of that, you can make an extended double ZEP. They are somewhat popular in VHF as verticals on towers like this. When you can concentrate the energy on the horizon, or the pancake gets flatter than with a regular dipole. So it's a way of getting gain without having traps and different things like that. So that's the EDZ. Any questions on that? I think I'm going to diverge, because there's a whole family of antennas related to dipoles. I'm not going to get into it much unless you have questions. But I like these antennas to play with. It's on the bottom of page 1. What's the topic here? Loops, right? Loops. What do we mean by small? Small is in terms of wavelengths. So if you make a dipole really short, like we did with that one with loading coils, you'll find you could make it really short, but you have to tune it somehow by adding something to the ends. So if you bend the dipole around in a loop and make it less than a half wavelength in circumference, you could put a capacitor in series with it and tune it. The smaller you make the loop, the bigger the capacitor has to be. And the current becomes almost constant, because you're like slicing that part where the current is high. It doesn't diminish over that great a distance as much as it would if it were a full-sized loop. So you're just bending a dipole around in a circle and making it physically small. So here's an example of one at 432 megahertz. Now on 20 meters, a loop like this might be this big around. You could fit it in your room. So that sounds pretty neat, because you could now have an antenna in your apartment that you would normally put on your tower that would have 30-something foot elements on 20 meters, and now you got a 2 or 3 foot diameter loop. Let's see if this works. Yes, it do. All right, and it's fairly omnidirectional this way. All right, very tiny. It turns out that if you put a little loop of wire in the middle that's about a quarter of the diameter of the loop, you can match it to 50 ohms, which is what they do on 20 meters. They have a little loop in the middle. Who makes those? You guys have one, right? A loop? Is it
Yeah, MFJ makes.
MFJ? Several people make them now.
Yep.
All right. What is the pluses of this?
The Alex loop.
Alex loop, right? Well, what's the pluses of this loop on 20 meters? The good features of it.
Low noise.
Low noise, very small, right? That's probably number one advantage. Think of it. What's the disadvantage of it?
Very narrow bandwidth.
Very narrow bandwidth. If I move from, say, 432 to 430 or 434, I'll probably lose it. And on 20 meters, you're talking less than the band. And I remember playing with an Alex loop and analyzing it. On 40 meters, the bandwidth was something like 7 or 8 kilohertz.
Yeah, not very wide.
In other words, you move more than a few kilohertz, you've got to retune this thing. So the expensive ones have automatic tuning adjustments. The cheap version, or the homemade version, probably has a knob that you turn it remotely. What's another disadvantage of this thing? Extremely high voltage. Now, I'm only running a few watts of power, but if I ran 100 watts, I could easily get 20 or 30,000 volts across the ends, only during part of the cycle. During the other part of the cycle, the current is high. So you got the worst of two things. The capacitor has to have very high current rating, and so does the inductor, and it also have to have very high voltage rating so it doesn't break down. Now, you normally don't buy parts like that. That's why they're expensive. In a lot of those loops, they'll say maximum power 10 watts. If you try to run a kilowatt into one, you'd probably fry it. I ran 100 watts into a homemade 80-meter one once, and I ran out of the room. The room lit up blue. It was like fireworks. It was fun, but you know, they're interesting. I made a 160-meter one, and I could light up a neon light with milliwatts from it, and that takes over 100 volts just to fire that. So they're kind of neat, but you got to remember they're called high Q devices, and they're very narrow bandwidth. Notice I can detune this very easily. In fact, if you even just going near it, you'll detune it, you know, because the body capacitance. So if you're willing to put up with that, you can have it. Now, another disadvantage is when the ham that's apt to use one of these in his apartment is also the ham that has to watch out for the fact that the field strength around you is very high, and it can be dangerous. So unless you're running really low power, you don't want to be too close to one of these things. So the people that tend to use them are close to them, so they got to watch out for their power rating. I'd like to build a kilowatt one. I think it'd be kind of neat. Maybe someday I'll do that. All right, so that's sort of an offshoot of dipoles. The new low frequency bands that we have, how many people have worked on those yet? Anybody here? 600 meters and 2200 meters. Those, some people are using loop antennas or shortened dipoles or monopoles to get on those bands, but I was thinking of making a giant loop out of some hardline, you know, to get on some of those bands with. All right. Long wires. Long wire is a dipole, but it's longer than a half wave. And it can be random in length, or it can be tuned. It can be a multiple of half-wave dipoles all added together. So I'm going to show you one of those. We already went through the ZEP and the double ZEP and all that. But the long wire doesn't have this phasing stub here. Let me find one. Well, here's a J-pole that's two half waves end to end. What do you think's going to happen? Get my whole little holder here. I'll make it, it's a full wave. What do you think will happen as far as the radiation pattern of it? Any guesses? It's a half wave added to a half wave. A null in the center. Let's see if that's true. Well, there is a null in the center. You got a peak there and a peak there. And there's the null, all right? And it can go around and do the same thing. In fact, I have 4 peaks. There's one. There's a null, there's another one. Think of a 4-leaf clover. This way, and that way, and that way. What's happening? Why is it doing that? Whereas the other dipole had this nice pattern perpendicular to itself. This one doesn't. In fact, at the horizon, where you want to talk to people, it's got a null. But overhead, there's a peak, and down into the ground, there's a peak, and likewise on the other side. This is not a good antenna if you want to talk to somebody on a nice low horizon. But it is okay if you want to talk to somebody at the right angle overhead or the right depth on a submarine down below. What is happening? The two currents are opposite because every half wavelength they reverse. So I show arrows going one way for half wavelength and the other way for the other half. The currents are out of phase with each other. At least broadside that way, it's not going to work. But in some other direction, because the distance from here to the source is now different, it's greater here than is there, they will add. So the out of phase parts will add in phase if you tilt at the right angle. There's some math involved there, which I'm not going to get into. So, for 2 half waves, or a full wave, whether it be fed at the end or somewhere in the middle, it's going to have 4 lobes of energy instead of too. It's going to have kind of like a cone going up around this way and another cone going on that way. Not good for this purpose, but it might be good in some direction that you want. It looks like a 4-leaf clover. All right. So I could make another one. This one is 3 half waves. And a lot of hams do this. I'm going to put a light on this one. Yeah, this is a red one, I think. Yeah, I'll keep it vertical. What the hey? Is it lighting up? It's got a null there. All right, there's a peak. Oh boy, I can't even see it. I think I'd better stick with horizontal. It'll be easier to deal with. There we go. So there's a peak. There's a little peak in the middle, and a little peak there. Bottom line is that now it's a 6-leaf clover. There's one peak, another, and there's another there. So we do have some energy on the horizon, but we also have some going up this way. This is the case when you take a 40-meter dipole and run it on 15 meters. A lot of people that I heard somebody say they were a novice. That was an old novice trick. Make a 40-meter dipole, run on 15 meters. The impedance is fairly low. It's not as low as the 70 ohms now. It's going to be higher. When you start adding wires in the end, the impedance goes up. But this current here is out of phase with this and in phase with that. So 2 out of the 3 are in phase with each other. So that means you're going to get some gain, but you're also going to get some signals in other ways. So you've got a 6-leaf clover coming off of this thing, or 3 cones, one being flat this way and one going this way and one going down. So if you want to run a 40-meter antenna 15 meters, beware that you may not have a clean pattern in the direction you want. You're going to be putting energy in other directions. All right, I can keep going on and on. I can make them longer. And what do you think is going to happen? Get more lobes, exactly. Let's see, I've got one here somewhere. All right, here's one that's fed. This is how many half waves? See the black line? Somebody can tell me. There's one. This black line represents the handle that I put on. There's another. There's 4 half waves. And I could feed it here, or I could feed it here, or whatever. This is typical of somebody just putting a wire out the window. If it isn't exactly a half wave, or a multiple thereof, you might need a tuner. But you always look at the far end of these things and work your way back towards the source. So when you look at the far end, we got what kind of voltage?
High.
Very high. What kind of current? Very low. I go a quarter wave down the line where the tack is. What's the voltage here?
Low.
Low current?
High.
High. All right, now I go up to here, another quarter wave. Voltage is?
Low. No, high.
High. All right. Every half wavelength, the voltage is high. The current is almost 0, right? Here the current is high and the voltage is low. Here the current is low and the voltage is high. Here where the tack is, the current is high. That's that neutral point, remember? You could touch it and I put a tack there because there's no high voltage there. So there's very high current, very low voltage. Here the voltage is high, the current is low. And here the voltage is high and the current is low. And somewhere between those two is the matching point for my light. The voltages are going up and down. Plus, minus, plus, minus. The currents are highest here, 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 here. But the arrows, the direction of current, reverses. So if the arrow is going this way, it'll stop and it'll go this way. And it'll go that way and that way. I have how many half waves? 4. 2 of them have currents going to the right and 2 have currents going to the left. So what do you think should happen? This is where the brain comes in. If you have 2 people, if you have a team of 4 people and 2 are pulling one way and 2 are pulling the other way, and they're both equally strong, what happens?
Nothing.
Nothing. Tug of war, right? You don't have an odd number, so they're going to be working against each other. So if all our thinking is true, then we should have some nulls and peaks. Let's see if it works. Well, this is so bright. I got too much power going in there that I can't get a deep null. I'm going to crank the power down to something useful. These LEDs are pretty sensitive. Here, I'll try running that and see what happens. Yeah, that's a little bit better. All right. There's a null. There's a peak. All right. A null, peak, a null, a peak. Notice the null right there. That's perpendicular or broadside to the antenna. As we surmised, there should be a null because the currents are out of phase. You've got two going one way and two going the other. If you had an odd number, at least it'd be something, because one would overtake the other two. Or I should say two would take the missing one. But when you have an even number, you have a null, just like you did with the double length one. But you're going to have lobes. You're going to have more lobes because you're going to have more directions where all these four things add up because the distances now become different. So instead of having the 4-leaf clover, we now have an 8-leaf clover. It's got 4 that way and 4 that way. All right. The more of these sections you add, the longer the antenna goes, and the more lobes of energy you get. This is the situation when you run the G5RV antenna. A lot of hams want one antenna that covers all bands, and it's just a piece of wire with some matching without any kind of devices to put them in phase. So you end up with all these lobes. So if you use a 80-meter G5RV on 10 meters, you're going to have 16-leaf clover. And if you're lucky, one of those lobes is in the direction of that rare country that you want. If you're unlucky, you'll spend all your time trying to work the 50th state out of 49 because it's off there somewhere and it's one of those nulls, you know. And maybe you'll wait till the propagation changes or something and you'll get it. So you can make these things long, but you look at the picture and you'll see these little lobes of energy in different directions, and there's all kinds of math behind it, and I'm amazed how these guys in the 1920s and 30s figured all this stuff out with these long wires. But see the arrows going in different directions. All right, so you can combine these. That's why my next part is. You can make these things longer and longer, and you can combine two of them, because remember those lobes are off on some side angle somewhere, right? And that angle, if you know what it is, you can match that to another antenna. All right, here's one of them right here. All right, everybody see that? All right?
Oh, you're in the way.
I'm in the way. So let's put it this way. It's bidirectional, by the way. You get lobes that way and that. All right, here's one lobe of energy. But I can also find another lobe off in this direction. So suppose I took two of these antennas and combined them in the form of a V so that the angles matched. So they're both shooting in the same direction. I would have what I call a V-beam antenna. And I have one here. These are all things that a lot of people on HF use because they're simple wires and you can hang them from towers. Field day people use them on 40 meters and so on. The trick is that this has to be more than a wavelength long, preferably 2 or more. Let's see if it works. The V-beam. It's pretty sharp. Is it lighting up? Yeah. Everybody see that? It's sharp. Look how good. I just move a few degrees and I lose it. I should put a little more power into it just because I'm standing a ways. And go back. So that's called a V-beam. And the longer you make the legs of the V-beam, the more lobes it has. So you're trying to reinforce 2 lobes, the 2 strongest. There we go. So there's the main beam, all right? Everybody see that? Look, I go not too many degrees away and I lose it. All right, and vertically it's a little broader. So you can get gain out of a couple of wires as long as they're a few wavelengths long. The longer the better. The narrower this angle gets because those lobes become more parallel to the wire when you do that. So if I'm reinforcing a lobe off of this one and a lobe on that one in the same direction, and the old handbooks have formulas and charts showing how many degrees to make this for how many wavelengths each leg is and all kinds of stuff like that. And this tells you here, it's how to make the thing 2 wavelengths per leg. So that's a V-beam. And if you don't like antennas, you can make a kite out of it, I guess. All right? Well, I'm going to go a step further. I'm going to take 2 V-beams, and this antenna is important because it's also on ham exams, and I'm going to make 2 of them end to end and make what's called a, anybody have any idea?
Quad.
Well, it's not a quad. It is 4 sides, but it's not a quad. A rhombic, all right? And I'm going to pull this out here. So this is two V-beams, and if you look at the picture, you'll see that the lobes from each of the four legs reinforce each other. And I had to, of necessity, make the legs longer, shorter on this antenna and that one, just so I could carry it. So this is kind of like a minimal size rhombic. I think it's a wavelength and a half per leg instead of 2. Let's see if it works. There, oh yeah, look at that. All right, there it is. Everybody see that? Now I can turn it around. It also works. What kind of a pattern is that? Bidirectional. There is a way of making a bidirectional rhombic into a unidirectional rhombic by putting it's called a terminating resistor. And that's this little thing here. This is like several hundred ohms. And let's see if this works. What it does is to rob power in one direction from being radiated. So the terminating resistor has to handle a good part, like a third of your power, because it's wasted, it's heat. But what it's doing is it's basically absorbing energy that's reflected. Let's see if it works. Back. Well, it works, but not perfectly. All right, it does knock it down, but not perfectly. All right. Oh, I know. I was touching the wire. That was. There we go. So it's got what we call front to back ratio. And if you adjust the resistor just right, you can make the front to back ratio infinite. And that's what they did in World War II. They had these rhombics up in remote islands in the Pacific, and they were pointed in one direction. They were so big and so sharp that if you moved one a few degrees, you wouldn't hear it. So it was to help keep from being eavesdropped on. And they would put terminating resistors that they would adjust carefully to get the front to back ratio down to 50 or 60 dB. And that's a lot. I mean, so that they could null out the signal on the back. We're talking about antennas that were huge, many wavelengths per leg. But I figured I did make my rhombic. That was one of my goals, my bucket list goals. So now I can fly a kite, right? All right, any questions on the rhombic? Terminated rhombic and unterminated. There's a question on the, I think the extra class or the general about that. There you go. Now you can visualize it.
Yeah, down in New Jersey there used to be a AT&T long wire for overseas phone calls, and they had giant rhombics out in the field.
Really?
Come up on 3 telephone poles.
Yeah. Oh, all of those long wires have signals that are out of phase with each other every half wavelength. So there is another way you can deal with that if you want. Instead of having them cancel, you can put little phasing stubs that bring it back in phase. And this is an example one. So now I've got 3 half waves, but instead of 2 going in currents in one direction and 1 out of phase with it, I can put the back all in phase by putting these quarter wave stubs. I think MFJ makes one with twin lead or ladder line or something for different ham bands. Am I right?
Yeah.
You need a lot of tower space. You gain a narrower beam width the more of these sections you have, but because they're half wave sections, so you don't get the full gain that you could because they're not far enough apart like the extended double ZEP would be. Let's see how this one is a light bulb, not an LED. Oh yeah, it's lighting up. All right, I'm going to make it vertical because this is more of a popular VHF antenna, 2 meters like this. All right, now it's got a signal on the horizon, see? And nothing here and here because I've got rid of those side lobes of energy off to the side by putting these in phase. All 3 are in phase. The currents are all in the same direction, but they're reversed in the stub. The stub doesn't radiate because the currents in each half of it are in opposite directions when they go around the corner, and the radiation cancel. And in fact, you could bend these around in the form of a circle if you want to save space on VHF. Like I've seen antennas like that. There are different ways of phasing. I think the station master antenna uses coaxial stubs inside of the fiberglass tube to put all the sections in phase with each other. And the gain that you get diminishes. The antenna has to be more than twice as long physically to get 3 dB. And if it's fed at the end, you lose signal from radiation. So there's less signal at the end than there is at the bottom when you do that, so you lose even more that way. So those antennas never have as much gain as you could possibly get, but they have to make them rugged and weatherproof and all that. So that's a phasing stub. Right, you'll see that word stub, stub matching. That's a question on the exam. Any questions on that? How to put the antenna elements in phase.
Getting kind of late now.
It is. You're right, it is. I'll show you a couple more and then you can ask questions because I got them right down here. I'm going to have you look at this. Two dipoles. We already did one of these with coax, but you can use transmission line. They are, is this broadside, collinear, end fire? What is it?
Broadside.
Broadside. Signals broadside of the plane. Notice that they're in phase this way because they have equal lengths of cable and null off the ends. They're half wavelength different. So this would be a good NVIS antenna if you want to mount it this way and the signal would shoot up overhead. So that's a broadside array. You can make another broadside array like this, where I'm end feeding the dipoles, so I have 4 dipoles instead of 2. Is this broadside, end fire, collinear? What is it?
Broadside.
It's broadside, but it's also
Collinear.
collinear because there's 2 end-to-end sections. So it's a broadside collinear, all right? And I've got another one which, notice the crisscross of the wires here. Broadside or end fire or collinear. And just like the one where we fed the 2 things out of phase and that signal is in line with the plane, so that makes it
End fire.
end fire. So when you crisscross the elements, you can pick it up that way, and if you don't crisscross them, you go that way. And let's see, a couple others here. There's several. There's a bobtail curtain. I'll show you that if you want interested afterwards. But there is one here. This is a little bit, you got to think about this one. Most hams would mount this vertically polarized on, say, 40 meters or something. Oh, yeah, there we go. This is called a bobtail curtain. There's a quarter wavelength. This is high voltage. This is high current. This is high voltage, low current. The currents reverse here and here. So this part and that part cancel as far as radiation. This part and that part cancel as far as radiation, but all 3 of these are in phase with each other. And since this is shared by both the 2 ends, the current in the middle is twice as high